3, 2, 1.
So today we will be speaking to Dr. Anuj Grover and getting to learn a little bit more about his work, his lab and the people that work there. So good morning, sir.
Good morning, Sunishka.
My first question to you today would be, could you tell us a little bit about your lab and the work that you do there?
My lab is called VLSI Circuits and Systems Lab. We call it VICAS. And in my lab, we primarily work on digital circuits and systems. And a lot of our work is driven by problems that we have in the industry. A lot of our work is on low power and error resilient designs. And we also work on a wide range of associated topics like how to manage mismatch, how to manage low voltage variations, how to manage IR drop, error resilience, radiation hardening, and a wide range of such topics. So I would say that in our lab we work very close to what a customer would need, and that's primarily because we are strongly influenced by industry, and a lot of our lab students work very closely with the industry.
Oh, okay. Sir, so could you also tell us a little bit more about the work that you do in the lab right now?
Okay, so in my lab, we primarily work in three major themes. One big theme is in-memory compute. Just to explain a little bit about it, in traditional computing systems, there is a computational or a processor, and there is a memory. Memory stores information, processor processes it. And there is a lot of data transfer that happens between the two. In advanced systems, where we have a lot of data transfers happening because of a lot of sensor data available, a lot of machine learning happening, a lot of artificial intelligence algorithms running on the system, this data transfer alone can take up to 30% of system power. When we do in-memory compute, then the memory kind of behaves like the human brain. A human brain stores information and also processes it. So in-memory compute does something like that, where we not only store information inside the memory, we also compute or process that information within the memory. We already talked about it being much lower power because data transfer is not required. It is also much denser because now memories are full custom circuits, and when you make other circuits around it which would otherwise be say machine driven or designed, and you convert them into full custom circuits, you save a lot of area. And the beautiful thing is that you also save or you also improve performance. So in VLSI there are three key things that we talk about: power, performance, and area. We call it PPA. So when you go for in-memory compute, you improve all three of them: power, performance, area. And I very commonly say that it's like पांचों उंगलियां घी में और सर कढ़ाई में. So it's a win-win-win on all the three axes for us. So that is one major theme that we are working on. Additionally, we are working on themes related to low power and graceful aging. So just like when we age, our responses slow down, probability of accidents increases, failures increases. Very similarly, when chips age, they also start to fail. And if we have these chips being used inside, let us say, a car, you do not want them to fail. You want them to continue to operate. They issue a warning, but you do not want them to fail at all. So in my lab, we are working on a range of designs which help in graceful aging. We are working on sensor designs. We are working on machine learning algorithms which can preempt the age or preempt the failure before it occurs, raise a warning flag, so that whenever your car goes for a service next, the engineer there can know and they can replace the chip. This prevents failures, this prevents accidents, this prevents loss of life and property. So this is another big theme that we are working on. Uh, Another theme that we are working on in our lab is around on-chip characterization. In advanced technologies, we have integrated a lot of devices onto us every single chip. Come to think of it, about 20 years back, the phone was just a calling device. Then came iPhone. It became a calling device and a music player. Then it had a touch screen. It had many more functions. Today's iPhone or today's phone have much stronger, much powerful processors than some of the laptops 5 years back. So when you integrate so much functionality onto a chip, testing it becomes a huge cost. And we need more diagnostics to be able to identify failures and prevent such failing parts from being shipped to the customers. So, this third theme that we are working on is about measuring uh, diagnostics on the chips so that we can preempt failures and not ship failing parts to the customers. So, that's the third primary theme. And then associated with these three big umbrella themes, there are many smaller projects that my MTech students take up, that BTech students in my lab take up. They could be linked to radiation hardened designs, error resilient designs, a wide range of associated topics also we work on.
So initially there was a little bit about diagnostics, preventative measures, and also a change in the way a chip functions itself by integrating memory onto it and doing the processing there itself. My other question to you would be, why all of these are low power? Why is low power that important?
Oh, low power is actually very important. Come to think of it, today electronics is very pervasive. You have pacemakers, they're embedded next to your heart, placed next to your heart. They have a battery associated with them. If the design of the pacemaker is not low power, then instead of replacing that pacemaker after, say, 10 years, you will need to replace it after 5 years. That's huge. Uh, that's invasive aspect of not having low power designs. But irrespective of that, uh, today the kind of computations that we do and the number of computations that we do is humongous. I was reading somewhere and we saw that the total number of computations that are happening in the world today are 180 times more than they were happening about 6 years back. So that many more computations would mean that much more power consumption. So if we do not become much more power efficient, then we are actually either we will not be able to do as many computations because the chips will become very hot, or if we are able to do as many computations by advanced cooling mechanisms, then we are having a huge burden on the environment. So low power is definitely necessary to support further advancement, further improvement in our quality of life, to ensure that we remain environment friendly or we become much more and more environment friendly as we move forward. So low power is not just about, as I mentioned, about the aspect of life. It is also about the aspect of bigger life in terms of the impact on the environment. So low power is a very key figure of merit for any product that we design, any product that sells. Your cell phone, the kind of life it would have in terms of on one charge, that's a very key selling point. A smartwatch, how long can you run it without recharging it? That's a key selling point. So uh, low power for many, many reasons.
Finally, I'd like to ask you, what have been the accomplishments in the past in your lab, and what do you see to accomplish in the future or focus in the future?
3 students in our lab have already won PM fellowship. So we have 3 PM scholars in my lab. What that means is that whatever fellowship they would get from their regular stipend, that is doubled up by the PM office. So this is a recognition, because only 100 scholars are recognized across the country for such awards. So 3 students in my lab have won such awards. Then in addition to that, we regularly publish in some of the best venues across the world. It's difficult to keep account of how many publications, how many patents we have filed, but they are a regular in our lab. So anyone interested can go to the website and find out more about those things. But yes, I think I'm happiest about the fact that we have 3 PM scholars from our lab, and this is a big achievement. In terms of going forward, I think we will continue to work a lot on in-memory compute. That's a up and coming field. There is a lot of decision making, a lot of work that needs to go into it, and it holds a lot of promise. As I said, you gain on performance, you gain on power, and you gain on area, all the 3 key axes. So we will definitely continue to work on in-memory compute. We will also continue to work on graceful aging, because what I have realized until now is that new phenomena of aging emerge as technology scales. So you need to be on top of all of them. And what is also important is that we need to make our algorithms more and more mature. So aging is another theme that we will continue to work on. And I'm actually very open to new projects coming from new industry partners, where if they have some particular need around subsystem design, memory subsystem design, BIST design, anything like that, we would definitely want to take them up and work on them.
It was very nice to talk to you today.
It was my pleasure, Sunishka.
And learning about your lab was very insightful, and it would be great if you could also go to the lab and speak to the people there as well.
Sure, let's go.
My broad area of research is in memory computing, in which they try to merge the compute and the processing clocks. So my work is on modeling on these IMC architectures, so that we can make good design choices for our implementations of our algorithms. So the key challenges is to that we need to make an accurate model of the IMC architectures, so that we can say that our model is accurate. We need to model all the nonlinearities in our model, and it will help the designer to make the design decisions at the earliest stages, which will enable him to save the cost as well as the time for the whole project.
IC testing or chip testing is no longer a back-end issue. It evolves into a front-end crisis, which needs a cost-effective and high-performance solution. So my active area of research is to test or to characterize the SoC or test chip over the various parameters or functionalities. As the technology is scaled, the complex IC may fail because of so many reasons. So I am designing on-chip solutions for in-depth characterization of SoCs, which can effectively characterize the dynamic IR drop, leakage current, temperature, delay, metastability issues, and so many reasons of failure mode. So this work is in collaboration with ST Microelectronics, and it's very interesting work. Recently, I have also been awarded by PM Scholarship.
In conventional approach to safeguard the system from aging-related degradation, we introduce timing margins. As the chips become slow, we add timing margins. However, in advanced node technologies, it is prohibited in terms of area, and it also significantly impacts power consumption and performance. I intend to carry out my research on this problem statement. Our objective is to predict the aging of an IC by establishing correlation between indirect aging parameters using machine learning and implementing a dynamic compensation mechanism to respond and adjust to aging.
My area of research is an analog IMC. In analog IMC, what we are doing, along with transferring information on the bit line, we are computing information as well. If we do the computation while reading the data, then we can easily improve the energy efficiency of the system. Earlier, we have completed the digital IMC architecture. Right now, we are on the edge of completing the analog IMC architecture. We have a quite good number of publications as well from my architecture. So we have patented 2 of our circuits. One circuit is filed as a patent and other circuit is in the process of filing patent. And I have multiple publications as well. One publication I have in AICAS, Artificial Intelligence on Circuit and System, which is a flagship conference of Circuit and System Society that happens in Korea. And other publication is in Indicon, one of the architecture that I have published in Indicon. And the last presentation, the last publication is in VLSID, which for which we have initiated the patent filing as well.
There are certain reliability mechanisms such as the HCI, the BTI effects, the TTDB, and etc. These they basically hamper the reliability of the ICs in the long run, and it leads to aging and other phenomena. So we need to have some solutions which are able to monitor these variations and also provide certain compensatory techniques so that we can control the effects. In my research work, basically I'm trying to design certain on-chip sensors like the interconnect sensor, the off-current monitoring sensor, the aging sensor, and I'm trying to integrate these sensors which will be picking data from its field of operation. It will be analyzing and processing data, and it will provide compensatory techniques such as the body biasing and the voltage scaling techniques to counter such variations. So to design and implement such solutions, I am working in collaboration with ST Microelectronics, and also I have been awarded the Prime Minister's Research Fellowship for the same. And I'm hoping and I'm trying to bring about certain significant value with the help of my research.